interpretation. Where does Riemann sum kick in? I think if you look up physics book, and they do a lot of this instantaneous analysis, and he's still appearing in the description of a general relativity, that this is a part of a physics intuition. All right, so here we have a VT, just like the example we have. And each time the velocity is changing. When you're driving a car, you have a speedometer, and it is showing when you actually start in the car, the velocity is constantly changing, right? But if it is a constant, if a velocity is a constant like this, let's say it's a v0, and then it's moving, 1 hour later, then it's really easy to understand the distance it traveled. I think that's the really easy part. If it is moving at a constant speed, vt, v0, and with a time period delta t, then distance it traveled, delta s, right, is simply that constant velocity times the time segment we measured, right? That's pretty much the definition of the velocity. If it's moving at a constant speed, we simply multiply this t, right? But the problem here is that the velocity is continuously changing, right? And the physicists do this a lot. Right, here's a t equals a, not the position a, but that position we have time assigned to t equals a. Here's a t equals b, and whatever the position we have there. And here's one instantaneous moment in there. And we have, let's say tk. You know where tk is coming from? In the context of Riemann sum, we divided the time interval to million pieces, for example. So we're dealing with some millionth seconds of b minus a, things like that. All right, that's tk. And what is the velocity there? Let's say it's a vk. But we have a formula, v, right? If you stick in that t equals tk, that tells you what the velocity is at that moment. That is the formula vt we have, right? And physicists like to do, all right, at that instantaneous time interval, velocity doesn't dramatically change. If that was a 10 feet per second, and millisecond later, it's still 10 feet per second, right? Very little change. So why don't we assume that from that moment to the next time segment, that we're going to call that displacement, delta sk, approximately, assuming this vk being constant, it doesn't change. It does very little change. Times the time interval. What is the time interval there? tk. That's the time interval, and between that time, the velocity changes, but it doesn't change that much. So why don't we just assume in that small time period, the velocity is a constant vk. Then, because of the constant assumption that we understand, we're just going to multiply the velocity to the time. Then that's a rough approximation of the displacement of the short time period, right? And there's a lot of question. You're being this careful in mathematics class, and then there's lots of question going into that, especially after you saw that sawtooth in the bottom of the equilateral triangle yesterday, right? The tiny thing can add up, and how do you know if this approximation is good enough or not? So there's a serious discussion of mathematics to justify this one, but let's just proceed. This is a physics intuition. This type of discussion actually turns people away sometimes from physics because you're unable to thoroughly understand if this is all correct or not. But we're going to switch to geometry. Maybe that'll give you the better idea. All right, if you accept, because in physics what happened is that you just trust the smart people when the smart people are talking, and you just accept it. And sometimes that will happen in physics. So all right, so that time period, so would that be okay? So if this is a millionth second and that's a displacement, it goes a little bit tiny moment, and next moment it goes a little bit tiny moment, delta S2, so that gives you the entire distance to travel. Does that make sense? Delta Sk is this displacement. Assuming that it keep going forward, then this seems like it measures the distance to travel. So you change this to, all right, that is k equals 1. What is delta Sk? That was Vk times delta Tk, right? What is Vk? It is V of T of k, and V of Tk times delta Tk, right? That is a physical intuition. If you approximate it instantaneous like this, and it seems like this must be the distance it traveled. But it looks a lot like Riemann sum, right? There's a function in this part entirely written in terms of tk multiplied by delta tk. So it is not equal, but what is the right symbol that goes here? Arrow, right? Limit of this one approaches, so it's not equal, right? So approaches what? This sigma symbol changes to stretch a symbol, and this vtk changes to vt, and delta tk changes to dt, right? And what is the time interval? A to b. Okay, that is one of physical intuition going into that, and probably that recovered the same result we had before. Understanding that, st derivative is vt, going backward, simple integral, and recover that. Make sense? All right, this is some physical intuition, but geometry kicks in the physics. So if you can understand the mathematical language of a geometry and physics together, it is really get fancy, and that's where we enter Maxwell's equation and general relativity and standard model and quantum physics. There are a lot of geometry in it. So we throw in the geometry. Let's look at it in geometric point of view. So here is what we looked at it before. Here is a v-axis, and here's a t-axis. We just looked at one graph before. Here's an arbitrary thing like that. Suppose we have this data from A to B, and we have one physical intuition in there, right? So integral from A to V of this graph and in here, Vt, is going to measure the displacement. In this case, there's no change of direction. Is that right? Because it's all above t-axis. So it's keep going forward. So the maximum velocity is really a lot, and here's a small velocity. It's going moving slow. Here's moving fast again. Things like that, right? What is the geometric meaning of this guy? Area underneath it, right? I don't know. When I first encountered this is entirely counterintuitive. What is this? The displacement has got to do with the area of this the curve of the VT. I just couldn't make that connection unless there is a fundamental theorem calculus. So you understand this area underneath it, the magnitude of the area underneath it, is really the displacement of this thing that's moving on according to this VT formula because of what? Fundamental theorem of calculus, right? But there is this gap. Wow, how do we actually reinterpret it without fundamental theorem of calculus to actually make sense out of it? Here's a physical intuition going in there again. So if you're in this part in here, I think it makes most sense. Here's a t k minus 1, and here's a tk, is little zoomed in version. And this height here is a vk, is that right? You tk plug into the vk. And what is this length here? It's a delta tk, right? And what was the meaning of a vk times a delta tk? That was a small segment it is moving according to the physical interpretation. But what is the meaning of this one in this geometry? Delta tk times this vk, right? And that was area of this one in here. That is the connection. Physical intuition describing vk times delta tk is a displacement, very tiny displacement, but in this picture that directly translates to the area underneath that curve. Therefore, if you keep doing that, you will collecting these tiny rectangles and over again. A tiny one. There is this lingering question: is this physics intuition? Is this error or tiny thing will add up eventually something significant, right? Because from this simple picture where up and down is simple like this, there's a way to understand it. For example, I want you to look at this top part, and here it's kind of constantly going down, right? And these are the error that we're concerned about, don't you think? These are the errors that is all involved. It's more like a triangular shape. But there's no overlap in terms of vertically, right? It's all stacked up like this. So I want you to slide that over here. Can you see that? The tiny thing was perfectly slided horizontally over there. And next error that we're concerned about. Do you understand what I mean by error? This is what we are actually calculating, but we're actually looking at this more complicated shape. So we're leaving that off in our calculation, right? So I'm collecting that error part in here and show that this is going to disappear. It's not going to add up to a significant amount. So the second one will be down here, something like that. So there's millions of this triangular-like shape is stacked up in here with no overlap, correct? No overlap. What is this thing here? This is always a delta t. if it's evenly divided by, right? And this thing here never changes the highest point. I'm going to say that it's a V star, some highest point there, and we're going to divide this time interval and smaller, right? So this is going to be on smaller and smaller, while this V star never changes. So the error is bounded by this V star that never changes times delta t, where delta t approaches what number? 0 as a tiny divided by tiny. So fixed number multiplied by very, very small number. And what can you say about this one? 0 approaching 0, something called by squeeze theorem, that error must approach 0 as it divided further and further. So typical shape we're dealing with like this, it perfectly explains that error is going to disappear. You don't have to worry about the error. But there are pathological examples of a function. The graph cannot be just simply understood like this. Did you hear about fractals? Yeah, if you look at the fractal shape, if you go zoom in and in, it never ends its complexity. So this argument fails right there. You can't divide it and look at it like that. But according to Riemann, that one is still integrable. That's where the surprise kicks in. And but for our nice world function like that, you don't have to worry about this. Physical intuition actually is correct, and there is some mathematical discussion like this behind it. All right, so we're going to enter Riemann sum again and again, and the book and myself will say that this is approximation, and this is guaranteed to be good. It's okay, and that we can't just do this all the time. You just have to trust, okay, and move on. But there's this thing to think about. If you're a careful thinker, then you have to think about things like this. All right, so that's that.